8 seconds. That's how long the United States sustained its most recent high-profile nuclear fusion reaction at ignition-level conditions. China just held plasma for over 1,000. On the surface, that sounds like a landslide, a technological humiliation even. One country can barely hold the reaction together long enough to blink. The other is approaching the scale of minutes. But that comparison, 8 seconds versus 1,000, isn't just incomplete. It's misleading in a very specific way, because those two experiments are not trying to solve the same problem. And if you don't understand that difference, you'll misunderstand where this race is actually heading and who's actually ahead. Here's the part that matters. Nuclear fusion is not one problem. It's a stack of problems layered on top of each other, and solving one doesn't automatically move you closer to solving the others. China's system, specifically the Experimental Advanced Superconducting Tokamak, or EAST, focuses on confinement, holding plasma stable, hot, and controlled inside a magnetic field for as long as possible. In January 2025, EAST sustained plasma at over 100 million degrees Celsius for 1,056 seconds. That's not a typo. That's nearly 18 minutes of maintaining a state hotter than the core of the sun. The United States, through the National Ignition Facility in California, is doing something entirely different. Instead of holding plasma in place, it compresses a tiny fuel pellet using 192 high-powered lasers, creating a brief but intense burst of fusion. In December 2022, NIF achieved ignition, producing more energy from fusion than the laser energy delivered to the target. A controlled release, but only for a fraction of a second. In follow-up experiments, that window stretched, but we're still talking about seconds, not minutes. So yes, one system lasts longer. The other crosses a threshold the first hasn't reached. And that's where things start to get uncomfortable, because the obvious scoreboard, time, isn't the one that decides who wins. Think about what a working fusion power plant actually requires. Not just heat, not just duration. It needs to produce more energy than it consumes, continuously, without destroying the machine that's containing it. That last part is where most of the optimism quietly collapses. Because plasma at 100 million degrees doesn't behave politely. It erodes walls. It destabilizes. It finds weaknesses in magnetic confinement systems that engineers haven't even predicted yet. Holding it for 1,000 seconds is an achievement. Doing it every day, reliably, inside a power grid, that's a different category of problem. And this is where the comparison starts to flip. China's EAST reactor is getting very good at holding plasma stable for long periods. That matters, deeply. You cannot build a commercial reactor without that capability. But EAST does not produce net energy. It consumes significantly more energy than it generates. It's a physics experiment optimized for control, not output. The US approach, on the other hand, has crossed the net energy threshold, but in bursts that are too short, too inefficient, and too expensive to scale in their current form. One can last, the other can produce. Neither can do both, yet. There's a tendency, especially in headlines, to reduce this into a geopolitical scorecard. China is ahead, the US is behind, or the reverse, depending on which metric you choose to emphasize. That framing feels satisfying. It's also shallow, because the real competition isn't about who can publish the more impressive number this year. It's about who is building a system that can close the loop, input, reaction, output, repeat, without collapsing under its own physics or economics. And right now, no one has done that. There's a detail that rarely gets mentioned when people talk about these breakthroughs: the materials. Inside a fusion reactor, the inner wall, called the first wall, gets bombarded by high-energy neutrons. Over time, those neutrons damage the atomic structure of the material itself, making it brittle, unstable, and eventually unusable. You don't just need a reaction that works. You need a machine that survives being near it. We'll come back to that problem later because it quietly dictates the entire timeline of fusion more than temperature or duration ever will. For now, just understand this. 1,000 seconds of stable plasma is not the same as a power plant. 8 seconds of ignition is not the same as a power plant. Both are fragments of a system that doesn't exist yet. And the country that figures out how to connect those fragments without the system tearing itself apart is the one that actually wins this. The question is whether that system even arrives on the timeline governments are publicly committing to. There's a quiet assumption built into most fusion coverage that once you achieve the physics, the rest is engineering. That assumption is doing a lot of work, because in fusion, the engineering is the problem. Take China's East reactor again. Holding plasma for over 1,000 seconds sounds like a solved stability issue, but look closer at how that stability is maintained. The system relies on extremely precise magnetic confinement, using superconducting coils, magnets cooled to near absolute zero, operating just centimeters away from plasma hotter than a star. That temperature gradient isn't just extreme, it's structurally hostile. You're asking materials to exist in two realities at once: cryogenic stability on one side, nuclear-level heat on the other. Over time, small imperfections become failure points. A slight drift in the magnetic field, a microfracture in a component, and the plasma touches the wall. When it does, the reaction doesn't politely stop. It disrupts violently. This is called a disruption event, and despite decades of research, no reactor has fully eliminated it. China is getting better at managing these disruptions. That's real progress. East and its successor projects are refining control algorithms, magnetic shaping techniques, and plasma feedback systems. But managing is not the same as solving. It means reducing frequency, not eliminating risk. And a commercial power grid does not tolerate systems that occasionally tear themselves apart. Now shift to the American approach. The National Ignition Facility looks cleaner on paper. No long-term plasma confinement. No delicate magnetic balancing act over minutes. Instead, a controlled implosion. Fuel pellet in, lasers fire, reaction happens, energy out. Except the inputs are absurd. Each fusion shot at NIF requires a precisely manufactured fuel capsule, often described as one of the most perfect objects humans have ever built. The spherical symmetry has to be nearly flawless, the outer shell uniform to microscopic tolerances. Inside, a frozen layer of deuterium-tritium fuel. Then, 192 lasers deliver about 2 megajoules of energy in a synchronized pulse lasting a few billionths of a second. The result? In successful ignition shots, roughly 3 megajoules of fusion energy released. That's the headline. Here's the part that gets buried. The facility consumes far more energy to power those lasers than the lasers actually deliver to the target. The total system efficiency is still deeply negative. So yes, the reaction produces more energy than it directly receives at the point of fusion. But the system as a whole does not. Scaling that into a power plant would require firing these laser shots multiple times per second. Not per day, per second. Each shot requiring a new precision-engineered fuel pellet, perfect alignment, and laser systems that can operate continuously without degrading. Right now, NIF fires maybe once a day, sometimes less. There's a gap here that isn't incremental, it's architectural. So you end up with two systems, each optimized in a way that creates its own bottleneck. China's model: continuous operation without net output. America's model: net output without continuity. Both are internally consistent. Both are incomplete. There's a third layer to this, and it's less discussed because it's harder to quantify: supply chains. Fusion reactors don't run on abstract physics. They run on very specific materials: rare earth elements for magnets, specialized alloys for reactor walls, tritium for fuel. And tritium in particular is a problem. It doesn't exist naturally in large quantities. It has to be bred inside the reactor itself, using lithium blankets that capture neutrons and convert lithium into tritium. That breeding process has never been demonstrated at commercial scale, not once. So even if you solve confinement, even if you solve ignition, you still need a self-sustaining fuel cycle. Otherwise, you're running a reactor that consumes a resource you can't reliably produce. China has been quietly investing in this layer, not just the reactors, but the upstream supply chains: lithium processing, rare earth control, industrial scaling. This is consistent with how it approached solar panels and batteries. Dominate the inputs, then scale the system. The United States has the research edge in certain high-end physics breakthroughs, but its industrial base for rapid scaling, especially in highly specialized manufacturing, has thinned over decades. That doesn't mean it can't rebuild it. It means it hasn't yet. There's a moment in most technological races where the question shifts. Not can this be done, but who can do this repeatedly, cheaply, and at scale? Fusion is approaching that moment, even if the headlines don't frame it that way. And here's where the narrative starts to get uncomfortable for both sides. Because the closer you look, the more it becomes clear that neither approach, on its own, leads cleanly to a working power plant. Which raises a more difficult possibility. What if the system that actually works doesn't look like either of these? Or worse, what if the timelines being publicly discussed, 2035, 2040, are anchored more in political necessity than engineering reality? We'll get into that tension next, because this is where the optimism starts to separate from the data. There's a number that shows up in almost every serious fusion roadmap. Sometimes 2035 if the speaker is feeling confident. Occasionally early 2050s if they're being careful. But the shape of the promise is consistent. Commercial fusion is close enough to plan around. That timeline exists for a reason. Governments need it. Energy systems are built decades in advance. Grids, transmission infrastructure, industrial demand, all of it depends on forecasts. If fusion is going to matter, it has to be penciled into those forecasts now, even if the underlying technology is still unstable. Which creates a subtle pressure, not to fake progress, but to frame it in a way that justifies continued investment. This is where things get complicated, because the technical milestones being announced are real. East did sustain plasma for over 1,000 seconds. The National Ignition Facility did achieve ignition. These are not exaggerated claims, but what they represent is often misinterpreted. Think about the materials problem we parked earlier. Inside a fusion reactor, high-energy neutrons don't just heat the walls, they change them. Over time, neutron bombardment displaces atoms within the material, creating defects. Those defects accumulate. Metals swell, crack, lose structural integrity. This isn't a maintenance issue, it's a life cycle limit. Right now, we don't have materials that can survive the neutron flux of a commercial fusion reactor for the kind of operating lifetimes required. Years, not months. There are candidate materials, reduced activation ferritic steels, tungsten composites, but none have been validated at the scale or duration needed. Testing them requires a working fusion environment, which creates a loop. You need a reactor to prove the materials. You need the materials to build the reactor. So projects like ITER in southern France exist partly to break that loop. ITER isn't designed to be a power plant. It's a physics and engineering bridge, demonstrating sustained fusion burn at scale and testing components under realistic conditions. But ITER is late, substantially late. Originally planned to begin operations in the 2010s, it's now targeting first plasma in the 2030s. Full deuterium-tritium operation comes even later. And ITER itself won't produce electricity for the grid. It's a stepping stone to demo-class reactors, which are the ones that might actually connect to power systems. If everything goes well, demo arrives in the 2040s. That's the optimistic path. Now layer this onto what China is doing. China is part of ITER, but it's also running a parallel track. Projects like CFETR, the China Fusion Engineering Test Reactor, are designed to move faster toward a demonstration power plant. The idea is to compress the timeline by iterating more aggressively. Build, test, adjust, repeat. That strategy works well in industries where iteration cycles are short. Fusion is not one of those industries. Each reactor is a multi-billion-dollar system. Each design change isn't a software update. It's a rebuild. So while China's approach might accelerate certain aspects, it doesn't eliminate the fundamental time cost of learning through hardware. Here's where the reversal hits. Up to this point, it might seem like a matter of patience. Keep funding, keep iterating, and eventually the pieces fall into place. But the closer you look, the more it becomes clear that fusion isn't just lagging because it's difficult. It's lagging because some of its hardest problems don't scale linearly with effort. You can double funding. You can triple the number of researchers. You cannot shortcut how materials behave under neutron bombardment over time. You can't simulate decades of atomic damage in a few months and fully trust the result. Time itself is part of the experiment. And that's not something governments can accelerate. There's also an economic layer that rarely gets discussed in detail. Even if you solve the physics and the engineering, the cost per kilowatt hour matters. Solar and wind, combined with battery storage, have been dropping in cost steadily. In many regions, they're already the cheapest form of new electricity generation. Fusion doesn't enter a vacuum, it enters a market. A fusion plant that produces clean energy but at a higher cost than existing alternatives doesn't get deployed widely. It becomes a niche, not a backbone. So the bar isn't just works. It's works reliably, at scale, and cheaply enough to compete. That's a much narrower window than most headlines suggest. At this point, the race starts to look less like a sprint between China and the United States, and more like a long negotiation with physics, materials science, and economics all at once. And none of those respond to political timelines. Which brings us back to that original comparison. 8 seconds, 1,000 seconds. Both real, both impressive, both in isolation insufficient. The uncomfortable possibility is that we're measuring progress in ways that feel concrete, but don't map cleanly onto the problem we're actually trying to solve. And if that's true, then the question shifts again. Not who is ahead, but whether the current paths on either side are even converging towards something that works. Remember the comparison we started with. 8 seconds, 1,000 seconds. It sounded like a scoreboard. It isn't. It's two partial answers to a question no one has fully solved. And at this point, the shape of that unanswered question is clearer than the answers themselves. A working fusion system has to do 4 things at once: sustain the reaction, produce net energy, survive the environment it creates, and do all of that cheaply enough to matter. Miss any one of those, and you don't have an energy system. You have a laboratory achievement. Right now, China is closer on one axis. The United States is closer on another. Europe, through ITER, is trying to bridge both. Private companies, Commonwealth Fusion Systems, TAE Technologies, Helion, are attempting variations that don't fit neatly into either government model. And none of them have closed the loop. There's a tendency to assume these paths will eventually converge, that someone will take the best parts of each approach and assemble a complete system. I'm not entirely convinced, because the constraints aren't just technical, they're structural. Magnetic confinement systems like EAST scale in one direction: longer duration, better stability, larger reactors. But as they scale, the materials problem intensifies, the cost rises, and the engineering tolerances tighten. You don't get to simplify as you grow. You inherit more complexity. Laser-based systems like NIF scale differently: repetition rate, efficiency, manufacturing precision. But pushing those variables simultaneously creates a different kind of pressure: industrial, not just physical. You're not just building a reactor. You're building a factory that feeds it, shot after shot, without failure. These aren't two roads leading to the same place. They're two different definitions of what working might look like. There's a quiet possibility that doesn't get much airtime, that the first commercially viable fusion system might not come from either of these dominant approaches, not from EAST, not from NIF, but from something that currently looks less impressive on paper: lower temperatures, shorter durations, smaller machines, but solves the integration problem more cleanly. History leans in that direction more often than people like to admit. Early leaders in a technology don't always define its final form. They define its boundaries. Now bring this back to geopolitics, because that layer never really goes away. China's advantage is not just in holding plasma longer. It's in system building, long horizon planning, state-backed industrial policy, control over key materials. If fusion becomes an industrial scaling problem, that model has real weight. The United States' advantage is different. breakthrough science, high-risk research environments, a private sector willing to pursue unconventional designs. If fusion requires a conceptual leap, a design that breaks from current assumptions, that ecosystem tends to produce it. Both advantages are real. Neither guarantees an outcome. There's also the question of timing, and this is where the conversation becomes less technical and more practical. If fusion arrives in the 2040s as a commercially viable technology, it enters a world that has already been reshaped by other energy systems. Solar, wind, advanced fission, grid-scale storage, they're not waiting, they're scaling now. So fusion doesn't get to define the transition, it joins it, late. That doesn't make it irrelevant. It might still matter deeply for heavy industry, for stable baseload power, for regions where renewables are less reliable. But it changes the role fusion plays, from primary solution to strategic complement. And that has implications for how much countries are willing to invest today. Because this is no longer just a scientific race, it's a question of return on time. Here's where I land, based on the data we have. Opinion. The current narrative overstates how close we are to fusion as an energy solution. The breakthroughs are real, but they're fragments, not a system. Treating them as near-finished progress risks distorting policy and investment decisions. Doubt. I'm not fully convinced that either dominant approach, magnetic confinement at large scale or laser-driven inertial confinement, can solve the integration problem without a significant shift in design philosophy. The missing piece may not be an incremental improvement. It might be something we're not prioritizing yet. Prediction. The first grid-connected fusion system that actually matters will arrive later than most official timelines suggest, closer to the late 2040s or early 2050s, and it will likely come from a hybrid or unconventional design rather than a direct extension of today's flagship projects. That brings us back one last time to the opening numbers. 8 seconds, 1,000 seconds, useful milestones, misleading conclusions, because the real clock hasn't started yet. The one that measures whether fusion can leave the lab and survive in the world we've already built. If you want to keep following where that line actually moves, not where the headlines say it is, you know where to find me.